odds ratios is that nobody knows what they are huge, but nobody knows what they are. You have two axolotls. How many other people knew what an axolotl was? Alright, they're not quite as obscure. How many people know about log odds ratios? They're exactly the same. So my analogy is apt. They're very cute. I was getting confused with it, I don't know. Throwing. Notion of a mapping from a log odds ratio to how strong that effect is. This particular mapping is going to depend on the domain, so I wouldn't take it too seriously, but it's at least a step toward getting calibrated. But that's enough of that for now. Onward to part 2. Okay, so we are going to start talking about quantifying precision. This is the question I got a minute ago. I've measured effect size, and I'm going to tell you that the Cohen effect size is 2, or I'm going to tell you that the log odds ratio is 0.8, and you want to know, how good is my estimate? How much might I be off by? And that is a perfectly good question to ask. So let me start with a different problem, which is that suppose you want to know how heavy people in the United States are, and you decide to do a telephone survey. So you choose random numbers from the phone book, you dial the numbers at random, and whoever answers the phone, you ask them, how much do you weigh? And you write it down, and now we want to try to say something about the US population as a whole based on that way of doing sampling. And my question for all of you is, what could go wrong with that methodology? So talk with a neighbor for a minute and see if you can enumerate all the things that could possibly go wrong. I don't want to interrupt your fun, but I'm going to interrupt your fun. All right, talk to me. What are some things that might be wrong with my methodology? Why is my answer going to be wrong? I hear liars. So people might not tell me the truth. Okay, that's one possibility. Yep. So people who are answering the phone in the middle of the day might not be representative. In what can you think of, like, some ways that they might be different? So the numbers are random. I don't necessarily know whether they're at work or at home. Okay. Yep. If I text first, why do you think I might get different results if I text or call? Because some people might be in the phone book or not, and that might tell you something about them, whether they're in the phone book or not. Yep. Do they still make phone books? Good. Anything else? Yes, so this is good because you're all telling me two things that are important. One of them is that the people that I get might not be representative, and you're telling me why that might change the answers that I get. Because sometimes you can have a non-representative sample, but it's still okay as long as there's no relationship between the ways that you are unrepresentative and the thing you're trying to measure. Yeah. So people might not be very accurate, maybe because they're lying or maybe just because they don't know exactly. Yep. Yes. Scale might not be calibrated. And it might be related to income, and many of the factors that we listed are related to income. And this is kind of one of the informal rules of social science, is that everything is correlated with income. Person might lie. Yep. Yep. Okay. So let me see. I put some ideas in the slides. So one of them, many of you mentioned examples of sampling bias where the sample is not representative. What that means, if the sample is representative, then every person in the population, in this case it's US adults, should have an equal probability of being in the sample. If they have different probabilities depending on what groups they belong to, then that's not a representative sample anymore. And if the thing that you're trying to measure is correlated with that group membership, then the results that you get will be biased. So that's sampling bias. But remember that there are two parts of that. There's a right level of skepticism. No skepticism is bad. Going crazy with skepticism is bad. It's almost impossible to get perfectly representative sampling. It's okay to be approximately representative as long as there's no relationship between group membership and the thing you're trying to measure. Sampling bias, some more examples. People mentioned that people who answer the phone in the middle of the day might be more likely to be unemployed. A whole lot of things that are probably related to income. So you guys mentioned several examples of that. You also mentioned examples of measurement error. Uncalibrated scale. Your question is ambiguous about whether you're asking for their weight clothed or unclothed. They might not remember their weight. They might misreport. The value neutral way to talk about lying is that they misreport. You might write it down wrong. Or one of the things that I run into in survey data all the time when I grab survey data is things get miscoded. So I did a study looking at, actually the height data that we looked at came from a very large study, 300,000 respondents. One of the problems with large sample sizes is that gives you more chances to make a mistake. They had a surprising number of people in that data set who were between 60 and 62 centimeters tall. I think there's only one person in the room right now who might have stepped out who is 60 centimeters. What do you think went wrong? Why were there so many? They were talking feet and inches. I bet there are a lot of people who are 6 feet 0, 6 feet 1. Not so many people, not so many adults. Oh, it could have been 62 inches, which is 5'2". Good point. Yep. The other thing that you see a lot is that missing data will sometimes be encoded as 99 or 999. So I did one study where I looked at birth weights for babies, and the mean came out to about 13 pounds. That can't be right. It's because I had accidentally included a whole bunch of 98 and 99-pound babies, which were respectively don't know and weren't asked or something like that. So, measurement error, lots of examples of that. Third thing, so we talked about sampling bias, that's number 1. Measurement error, that's number 2. Number 3, random error, which is just the fact that you collected a sample rather than the whole population. And so if you only call 3 people, then it's pretty clear that you might, just by chance, get 3 heavy people or 3 light people. and your estimate might be off just because of random sampling from the population. So those are the three big sources of error: sampling bias, measurement error, and random error. Usually, sampling bias is hard to quantify, often because if you knew what was happening, you would fix it. So you might not know it, and even if you know it, you might not be able to measure it. Measurement error is sometimes quantifiable. There are some ways to do that. For example, if you have two different processes, and one of them is more accurate than the other, you can use the difference between them to estimate how imprecise the two estimates are, the two measurements are. So the second one can be quantified. Third one, random error, turns out to be the easiest one by far to quantify, and therefore it is the one that we spend all of our time in statistics focusing on and completely ignoring the first two. Despite the fact that in practice, it is almost always the case that those first two are much more important than the third one. But the third one is easy, so we do it. That is my warning about everything that I'm about to tell you. I'm not the only one. Edward Tufte agrees with me and managed to express it in 140 characters. Random error is but one of 20 threats to learning from data. It gets disproportionate attention because it is the only threat that can be mathematically modeled. So, let's mathematically model it. Let's get back into the notebooks. If you will open up sampling.py, read through it, run the code, work on the first exercise, and stop when you get to stop here. Okay, we have a fix for the problem that we were having with the interaction. If you find this function called plot sample stats, search for that function, plot sample stats, and add this line at the end, pyplot.show. You can make the show explicit. That should allow you to do the interaction. And now, if you move the slider back and forth, it will update in place. So if you had that problem with interaction, give that a try. Hopefully that solves it. This is in the function that is called plot sample stats. Add this line. I want to go over a couple of things in the notebook. One of them is the distribution of weights for adults in the US is approximately a log normal distribution, which is kind of a funny shape. We're used to things like physical measurements on people and animals. Many, many things have a Gaussian distribution, which is this nice symmetric bell curve. The log normal distribution is not symmetric. It looks like this. It has a long tail on it. So there's sort of a central tendency around 60, 65 kilograms, but then there are heavy people who are up into the 120, 160 kilogram range. Turns out there's a reason for this distribution. At birth, the distribution is pretty close to Gaussian. And then as we become adults, it becomes log normal. If you are curious, I have a footnote in my book which explains why this is true, but it's outside the scope of our current activity. So I'm going to assume temporarily that we know what this distribution is, and I'm going to come back later and undo that assumption. But for now, assuming that we know what the distribution is, we can run simulated experiments that says, what if I took a sample of 100 people and I computed their average weight? And then I took another their average weight. Experiment to the next. So that's how we're going to quantify the precision of the estimate, which is by pretending that we did the experiment many times and seeing how different it is from one experiment to the next. Now, the thing about this example that is going to become confusing in a couple of minutes is the difference between n and iter's. So n is the sample size, and that's really important. That's the number of people that I'm going to go out and measure. And what we're going to see very soon is that as the sample size gets big, my precision gets better and better. When my sample size is small, no surprise, my precision is not so good. So n is the thing that really matters. Now, to estimate precise my estimates are, I'm going to run lots and lots of simulated experiments, and I'm calling iters is the number of times I run the experiment. That doesn't matter very much. It just needs to be reasonably big. As long as iters is big enough, I'm going to get a good description of my uncertainty. So iters, I arbitrarily choose 1,000 just because computationally it doesn't take very long, and it's big enough that I'm going to get answers that are close enough. Okay? So n is important, that's the sample size. Iters is just the number of simulated experiments that I'm going to do. So there's just taking one sample and computing one sample statistic, and now here, compute sample statistics is the function that runs lots of iterations, and I'm using a Python list comprehension there just as a syntactic way of kind of like a faster for loop. This example. Okay. Now, this distribution is the important part of the whole thing. This is, I ran 100 experiments. No, I ran 1,000 experiments. And for each experiment, I computed the estimated mean of the adult population, and I plotted it. So one time when I ran the experiment, I got 72. And one time when I ran the experiment, I got 74. And then there was that crazy time that I got 68. And then other crazy time that I got 77. And I just plotted them all. And this is showing me how much variability there was from one experiment to the next. Okay. This thing is called the sampling distribution of the mean. It's telling me how much my estimated mean will vary each time I run a sample. The question is whether it is a normal distribution, and the answer is it is going to asymptotically become a whole lot like a normal distribution. Even though I'm drawing from a log normal distribution, it is nevertheless the case that as my sample size increases, this thing is going to look more and more like a Gaussian. Because, anyone? That is the central limit theorem that I just invoked. Now, remember what the question is that we're asking, which is I've estimated the population mean, and I've said that it's 72 and change, 72.5, let's say. Now, you ask me, how certain are you about that? One way for me to answer that question is to show you that distribution. I could show you the whole thing and just say, it's like that. I think it's probably about 72, but it might be as high as 76. It could be as low as 68, but I'm pretty sure it's somewhere in that neighborhood. That would be fine. But if you want me to boil it down to a number, there are two ways I can do that. One of them is I can compute an interval, and what I might do is like chop off the lowest 5% and the highest 5% and show you the 90% in the middle. That would be a 90% confidence interval. And that's a way of taking this whole big blue distribution and boiling it down to, in that case, just two numbers. And I think I computed them here. So the confidence interval is the interval that is between the 5th and the 95th percentile. That'll be the 90% confidence interval. It is between 70 and 75 kilograms. And if you want me to give you a measure of my precision, I could instead of computing an interval, I could take the standard deviation of that thing. The standard deviation of that thing is called the standard error, and it is, loosely speaking, it's about how much I expect to be off by. So I could put this into a plus or minus. I could say, I'm going to be off by about 1.6 kilograms. So one way I could report this result is I could say, pretty sure it's about 72 plus or minus 1.6. So that would be the standard error.